Hello class, in this video I shall be discussing with you about the packing efficiency for hexagonal close packing arrangement. It is also known as HCP. As you can see on the board, the diagram of the hexagonal unit cell is like this. Okay, so moving on to the next step, let R be the radius of each particle, okay, each particle or spheres, okay, and here you can see the height be h, okay, height of the hexagon, and the side of this one, okay, be 2r. If it is a, then also it will resemble as 2r, so we need not take a again, we just take 2r, okay, everything in the form of radius, okay. And now see, we have to find out the volume, okay, volume of each particle as well as the volume of the unit cell, okay. So let us first see the number of particles present in one unit cell, that is of the hexagonal close packing arrangement, okay. So number of particles or spheres in HCP is equal to, okay, or say like in HCP unit cell will be equal to, okay, let us see here. See, there are 12 atoms present at the 12 corners of the hexagon, okay. So 12 atoms or 12 particles, and each of the particle contributes how many part of its share to one unit cell. That is, we can see here, suppose for example, okay, I will just show it to you in the two-dimensional, like this, okay. This is one of the layers. So the atoms are present at each corner like this, here, 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 okay. So see, one atom is sharing with 3 unit cell. This is of the one layer. Then on top also there will be another layer like this, with which this atom might be sharing again, or this atom will be sharing. So therefore all total, downside 3 unit cell, upside 3 unit cell. That means these 12 particles or atoms are sharing with 6 unit cell. Therefore it contributes only 1/6 of its portion to one unit cell, okay. Then the next one is 2 particles or 2 atoms on the faces, but only on the 2 faces. So here they contribute half of its share, okay. So only 2 are there, and each of the particle contributes only half of its share. Therefore it will be 2 into 1/2 plus 3 atoms on the body center of the unit cell, so that therefore they completely contribute, okay. Therefore it will be total number of 3 we write. Hence number of particle present in this HCP unit cell is equal to, we shall divide 6, 1 are 6, 6, 2 are 12. So 2 plus this one becomes 1, 1 plus 3 is equal to 6. So that means the total number of particle present in one unit cell is equal to 6, okay. Next one, since we have to find out the volume of both the particles as well as the unit cell, so I shall move on to the next one, that is volume of the unit cell, volume of the particles or sphere, okay. So volume of 6 spheres is equal to 6 times of, and each of the particles are taken in terms of spheres, so it will be 4/3 pi r cube, okay. So 3 1 are 3, 3 2 are 2, 4 are 8, so it will be 8 pi r cube. This is the volume of the 6 spheres, okay, 6 spheres. Let me just note it down somewhere here, that is the volume of each particle or say sphere is equal to 8 pi r cube, okay. Now the next one is the volume of the unit cell. Okay, so we shall deal it one by one. I hope it is done. Yeah. Okay, now normally suppose you have a structure of a cylinder. Okay, to find out the volume of the cylinder, what we do it this way: volume is equal to length or height. Okay, height into area of cross section, one of the area of cross section. Okay, this is how we find out the volume of any object. Okay, so here also we will apply that same method. Here also it will be volume of the HCP unit cell will be equal to the height into one of the area of cross section. Okay, so area of cross section. Okay, this is how we are going to find out. So you may not write this one, just for your understanding. Okay, let me show it to you here. Okay, volume of HCP unit cell is equal to height into area of cross section. Okay, now remember that we have to represent all the values, that is height as well as the area of cross section, in terms of radius. So now we shall find out the values of height of the unit cell and the cross section, okay, area of cross section separately. So let's first find out the area of cross section, that is area of cross section is equal to, so as you can see here, this is the area of cross section, okay, either up or down. Okay, so now if we divide this one into 6 equal parts of triangle, okay, and each triangle we know that it will give an equilateral triangle. Okay, so the area will be 6 times of the area of one equilateral triangle. So the area of an equilateral triangle formula, we know it is √3 by 4 a square. Okay, a is the side, so here in this case the side is 2r, so we write 2r and square. Okay, then this one you can write 6 √3 by 4, 2 to a 4 r square, 4 cancels, so we get 6 √3 r square. Okay, this is the area of cross section, so I'll just write it down here, 6 √3 r square. Now the next one we have to find out is the height of the unit cell H. Okay, height of the unit cell H. Okay, suppose, okay, let us extract this one, this atom, this 3 and this one, so all total 5 atoms I extracted out here. Okay, and we know that this is the height. Okay, so say suppose point P, point R, P to R is H. Okay, and Q is the midpoint of PR, then we can write it is equal to 2 times of PQ, isn't it? Height is 2 times of PQ. Okay, so therefore now we have to find out the value of PQ. Okay, and actually we have to represent in terms of R. So let us see here in this diagram, suppose these 3 atoms. Okay, these 3 atoms are like this, they form an equilateral triangle. Okay, if we join the midpoints of the sphere, they form a midpoint, and we know every sphere is having r as radius, so the total distance from here to here will be 2 times of r. Okay, 2r, and it is an equilateral triangle, so all the sides will be having 2r. So from there we shall extract out, so this portion I have shown you here, a b c. Okay, a b c, and Q is this point. Okay, so here you see in this point, if I draw like this a perpendicular line, okay, in triangle AQC, if I draw a perpendicular line, then it will divide the side AC into 2 equal halves. Okay, and this this line will make this side 30, this side also 30 degree. Okay, so now you see. After this, let us go back again here and see this particular triangle, that is P, Q and C. Okay, because we must know the value of PQ, so I'm going this way. Okay, now there is a gap. Okay, you can see the gap in the figure, but in reality there is no gap. Okay, I have just separated from them. So this atom is exactly on the top of the three atoms. Okay, it is in touch with, okay, this three atom, and if this from this to this is 2r, then from the upper atom or particle to the atom that is below, or a particle that is below, will also have that same distance as 2r. Okay, so that means, see, the distance between the center of this atom and this atom will be 2r. That is, PC is also 2r. QC is not going to be 2r. That value only we have to find out. Okay, QC we have to find out. If we find out QC, okay, then we will know what is the value of PQ by Pythagoras theorem, because it is a right angle triangle. Okay, so straight away going to this triangle. Okay, in right triangle QDC, okay, the given values are CD equals to R and angle DCQ equals to 30 degree. Now as you can see, with respect to this 30 degree, CD is the base and QC is the hypotenuse. Okay, and QC is what we have to find out. Okay, now which trigonometric ratio is having the relationship of base and hypotenuse? Okay, it is cos theta. Okay, or here theta is 30 degrees, so we write cos 30 degree equals to base by hypotenuse. So base is CD by QC, and cos 30 degree value is √3 by 2. We know CD is R. Okay, and QC is what we have to find. Then you just cross multiply and we get like this, 2r by √3. So this is the value of QC. Again, we use this value of QC for this triangle PQC. Okay, in right triangle PQC by Pythagoras theorem. Okay, you have to write in full form. So what we get is, see, PC is the hypotenuse, PC square is equal to PQ square plus QC square. We don't know this one, so you take it to other side. PQ square equals to PC square minus QC square. Okay, now PQ square equals to PC value is 2r. Okay, so 2r square minus QC value is this one, 2r by √3. Okay, so I write 2r by √3 the whole square. Okay, I'll round this one. Then we shall solve this one. This one comes 4r square, this one comes 4r square by 3. So PQ square equals to 12r square minus 4r square. Okay, like this. Then the next step, it will be this one, it will come to 8r square by 3. Then we transfer the square to the other side, it will be 8 by 3r square, so which will be 2√2 by √3r. Okay, so this is the value of PQ. Now we know the value of PQ already, so we put here. Okay, so height of the unit cell H equals to 2 times of PQ, that is 2 into 2√2 by √3r. So we get 2 to a 4 √2 by √3r. This is a height of the unit cell. Then we put the values of height and area of cross section in the volume. Okay, so you write again this one in the next step. Okay, so height is this one, 4 root 2 by root 3 r multiplied by area is 6 root 3 r square. Okay, root 3 gets cancelled, isn't it? Then 4 6 are 24, root 2 and r into r square, it will be r cube. So this is the volume of the unit cell. Now the next one we have to find out is packing efficiency. Okay, so packing efficiency equals to volume of 6 spheres divided by volume of unit cell. Okay, and that unit cell is in HCP and multiplied by 100. So the volume of 6 spheres, it's here, that is 8 pi r cube, and volume of unit cell is 24 root 2 r cube. So r cube gets cancelled, 8 1 are 8, 8 3 are 24. So we get, and yeah, one more thing, multiplied by 100, then we get here pi by 3 root 2 multiplied by 100. So 3.143 into 1.414 and multiplied by 100, we get 74%. Okay, so that is a value for the hexagonal closed packing arrangement. Okay.